Today, I want to tell you a story that starts with something very small and very ordinary. A simple daydream. Einstein imagines a man falling off a roof. That's it. No equations, no blackboards, just a thought. But if you follow that thought carefully and you refuse to let go when it starts to get strange, something amazing happens. That one idea leads you to black holes, to time slowing down, and to space itself bending. You discover the world isn't flat. It isn't neat. And it isn't very well behaved yet. It's curved. It's weird. And it plays by rules that almost seem to enjoy surprising us. And by the end of this story, you'll see why this strange little daydream became one of the most beautiful ideas we've ever had. I want to tell you a story today about a disaster, quiet disaster, a disaster that happened entirely inside the mind of one man while he was sitting at a desk in a patent office in Switzerland. You see, at the turn of the century, around 1900, physicists were feeling pretty good about themselves. We thought we had it all figured out. We thought we had the owner's manual for the universe. We had the laws of heat. We had the laws of electricity. And most importantly, we had the laws of motion. And the man who wrote that manual, the giant upon whose shoulders we were all standing, was Isaac Newton. Newton was marvelous. He was probably the smartest man who ever lived. He looked at the moon going around the earth, and he looked at an apple falling from a tree, and he had the imagination to realize they are the same thing. He gave us a law, a beautiful, simple rule. You probably learned it in high school. Force equals G times the mass of one thing times the mass of the other thing divided by the distance squared. And it worked. It was perfect. With this one little equation, we could predict where Jupiter would be in 100 years. We could predict the tides rising and falling. It was a clockwork universe. Everything ticked along exactly as Newton said it would. But there was a ghost in the machine. There was a tiny, nagging problem that Newton himself knew about, but nobody else wanted to talk about. And the problem is this. How does the Earth know the sun is there? Look at the solar system. Here's the sun, burning, huge, a giant ball of gas. And here's the Earth, 93 million miles away. And in between them, what is there? Nothing. Vacuum. Silence. Cold. So how does the command to turn get from the sun to the Earth? How does the sun tell the Earth, hey, I'm over here, curve toward me? Does it send a letter? Does it send a radio wave? Does it have a long, invisible rope? Newton didn't know. He assumed, and this is the critical part, he assumed that the connection was instant. He assumed that gravity was like a stiff rod connecting the two. If you wiggle one end, the other end moves immediately. He called it action at a distance. And to be honest, he hated it. He wrote letters to his friends saying, this is absurd. How can a body act where it is not? But the math worked, so everybody just shut up and calculated it. But then in 1905, a young man named Albert Einstein came along, and he broke the machine. Einstein had been working on electricity and magnetism, what we call special relativity. And he discovered something fundamental about the structure of reality. He discovered that light has a speed limit, 186,000 miles a second. Now that is fast. It is very fast. It is fast enough to go around the world 7 times in one snap of your finger. But it is not infinite. It takes time for light to travel. It takes about 8 minutes for light to get from the sun to the earth. And Einstein said something even bolder. He said, nothing in the universe can travel faster than light. No object, no signal, no information, no telepathy, nothing. The speed of light is not just the speed of a photon. It is the speed limit of cause and effect. You cannot affect anything else in the universe faster than the time it takes light to get there. Now, put these two things together. Newton says gravity is instant. Einstein says nothing is instant. We have a catastrophe. Let me give you a thought experiment. This is the experiment that kept Einstein awake at night. I want you to imagine a magician, a cosmic magician. And this magician snaps his fingers and poof, the sun vanishes. Gone. It disappeared. No mass, just empty space. Now, according to Isaac Newton, what happens to the Earth? Look at Newton's equation. F equals G times M divided by R squared. Does it have a letter T for time in it? No. It relies only on the mass right now. So if the mass becomes zero, the force becomes zero instantly. So according to Newton, the very instant the sun vanishes, the Earth should fly off in a straight line into the dark. The Earth should know immediately that the sun is gone. But wait, Einstein says nothing. Travels faster than light. Light takes 8 minutes to get here. So if the sun vanishes, we on Earth won't know about it for 8 minutes. We will still see the sun shining in the sky. We will still feel the heat on our faces. We will still see the shadows on the ground. For 8 minutes, the sun is effectively still there for us. The information that the sun is gone has not arrived yet. So look at the contradiction. Are you telling me that the Earth would fly out of orbit while we can still see the sun sitting there? Are you telling me that the gravity message arrived before the light message? That implies that gravity traveled faster than the speed of light. That is impossible. If you can send a signal faster than light, you can break the order of time. You can send a telegram to the past. You can kill your own grandfather before you were born. The whole logic of the universe falls apart. So Einstein realized Newton must be wrong. He wasn't just a little bit wrong about the numbers. He was philosophically wrong about how the world works. The Earth cannot fly off instantly. For 8 minutes, the Earth must continue to orbit around a sun that does not exist. It must orbit a ghost. It must dance around an empty spot in the sky simply because the news hasn't arrived yet. So the question became how? How does the gravity get from there to here? If it can't be a rigid rod, if it can't be instantaneous, what does it mean? It must be something else. It must be a ripple, a wave, a distortion in the environment, something that travels across the empty space, taking its time, obeying the speed limit, carrying the message, hey, the sun is over here. And this realization that gravity is not a magical instant connection, but a physical process that takes time, this forced Einstein to throw away the old rule book. He had to reinvent the entire universe. He had to find a way to explain how a rock can communicate with another rock across empty space without touching it. And to do that, he had to have what he called the happiest thought of his life. So Einstein is stuck. He knows Newton is wrong. He knows that gravity cannot be a magical instant force. It has to be something else. But what? He sits in his chair at the patent office in Bern. It is 1907. He is supposed to be looking at patents for electric motors, but he is staring out the window, and then suddenly it hits him. He has a thought so simple, so beautiful, that he later called it the happiest thought of my life. He imagines a man falling off a roof. Now, don't worry, in Einstein's imagination, there is a big pile of hay at the bottom or a safety net. The man is perfectly safe. But think about the man while he is falling. I want you to really put yourself in his shoes. Imagine the man wakes up and he is falling through the AIR. And imagine he pulls his keys out of his pocket and lets go of them. What happens and what? Do the keys fall to the ground faster than him? No. Galileo taught us that everything falls at the same speed. Heavy things, light things, they all go down together. Do the keys stay up in the air above him? No. To the man, the keys just float right next to his face. If he tries to pour a glass of water, the water comes out of the bottle and forms a floating ball. It doesn't fall down past his knees. And the man himself, does he feel the heavy No, he feels weightless. He feels like an astronaut. If he closes his eyes, he cannot tell that gravity is pulling him. As far as he is concerned, gravity has vanished. By simply giving in to the fall, by surrendering to the pull, he has canceled out gravity perfectly. Einstein realized if a person falls freely, he will not feel his own weight. This is a clue, a massive clue. It suggests that gravity is not some painted-on force that is always attached to you. It is something that can be erased just by moving in the right way. Now, Einstein flips the picture. He says, okay, if falling makes gravity disappear, can I make gravity appear out of nothing? Let's play a game. I want you to imagine you wake up in a box, a painted room, no windows, you cannot see outside. You're floating in the middle of the room. You have no weight. You assume you are in deep space, far away from any stars or planets. Zero gravity. It is silent. It is still. Now, suppose I attach a huge hook to the top of your box, and I attach a rope to the hook, and I attach the rope to a rocket ship, and I turn on the engine. The rocket starts to pull the box up. It accelerates faster and faster. Let's say it accelerates at exactly 1 g, 32 feet per second squared, the same rate that things fall on Earth. What happens to you inside the box? Well, the floor of the box rushes up and hits your feet. Wham! Suddenly you are standing on the floor. You feel pressure on the soles of your feet. You feel your legs holding you up. You feel weight. Now you take a ball from your pocket and you drop it. What actually happens? Well, you let go of the ball. The ball is just floating there in space. It has no forces on it, but the floor is accelerating up towards the ball. So the floor smacks into the ball. But to you, inside the box, it looks like the ball fell down and hit the floor. You look at this. You feel the weight in your legs. You see the ball fall. And you say, aha! I must be sitting on the earth. Gravity is pulling me down. But you are wrong. There is no gravity. You are in deep space. You are just accelerating. But here is the kick. Here's the thing that makes your brain hurt. Is there any experiment you can do inside that box to prove you are moving? Can you find a difference between sitting on Earth and accelerating in a rocket? Einstein thought about it. He thought about pendulums. He thought about springs. He thought about dropping weights. And he realized, no, there is no difference. The physics is identical. Nature does not know the difference between gravity and acceleration. If you are pushed into your seat because you hit the gas pedal in your car, or if you are pushed into your seat because you're sitting on the planet Jupiter, it is the same sensation. It is the same physical law. This is called the principle of equivalence. And this was the key that unlocked the universe. Because Einstein said, if I cannot distinguish between gravity and acceleration, then they must be the same thing. Gravity is not a force pulling you. Gravity is indistinguishable from acceleration. And this gave him a way to predict the future. He said, okay, I don't know much about gravity yet. It's mysterious, but I know everything about rockets. Rockets is simple mechanics. So if I want to know what gravity does to a light beam or to a clock, all I have to do is figure out what a rocket does to a light beam or a clock. Whatever happens in the rocket must happen near the Earth because they are the same thing. So Einstein sat down to imagine what happens if I shoot a laser beam across a moving rocket ship. And what he found changed our understanding of reality forever. So we have this crazy idea, the principle of equivalence. We said that sitting in a room on Earth is exactly the same as sitting in a rocket ship that is speeding up. Nature can't tell the difference. You can't tell the difference. If you drop a ball in the rocket, it hits the floor. If you drop a ball on Earth, it hits the floor. It is the same physics. Now Einstein says, if this is true, if this is really a law of nature, then I can use the rocket to find out things about gravity that Newton never dreamed of. Let's do an experiment. We are back in our rocket ship. We are way out in deep space, no stars, no planet, just us and the engine. The engine is pushing us up. We are accelerating. And I have a flashlight, or better yet, a laser, a pointer. And on the side of the rocket, there is a little window, glass. I'm going to shine the laser beam through the window. It is going to shoot across the room horizontally and hit the wall on the other side. Zip across. Now let's look at this from 2 points of view. This is how relativity works. You have to look at it from the outside and then from the inside. First, the outside view. Imagine a man floating in space outside the rocket, watching us through the glass. He sees the laser turn on. A photon. A little bullet of light leaves the flashlight. Now, once light leaves the flashlight, it is free. It has no connection to the ship anymore. It travels in a perfectly straight line. Newton says so. Maxwell says so. Light goes straight. So the man outside sees the bullet of light go perfectly straight across space. Second, the inside view, you are inside the rocket. But remember, the rocket is accelerating up. While that little bullet of light is traveling across the room, what is the room doing? The room is moving up. The floor is coming up to meet the light. So the light enters the window here. But by the time it gets across the room, the wall has moved up. So the light doesn't hit the spot directly across. It hits a spot lower down on the wall. Do you see? The light entered at eye level, but it hit the wall at knee level. I am exaggerating the speed, of course, but the principle is real. Now imagine you are inside. You don't know you're moving. You think you're just standing still in a room. You turn on your laser. You aim it straight across, but you see the beam go down. You see the beam curve towards the floor. It makes a parabola, just like a tossed ball. You would say, my God, the light is falling. Something is pulling the light down. Now here is the punchline. Here is where Einstein earns his pay. He says, if the rocket bends light, and if the rocket is the same as gravity, then gravity must bend light. If you stand on the earth and you shine a laser beam, the gravity of the earth must be pulling that light down toward the floor. Just a tiny bit, but it must be happening. Now stop and think about why this is so disturbing. Think about Isaac Newton again. Newton said gravity is a force that pulls on mass. F equals G times M divided by R squared. M is mass. If you have a rock, gravity pulls it. If you have a feather, gravity pulls it. But a light has no mass. Light is weightless. It is pure energy. If you put a sunbeam on a scale, it weighs 0. If M is 0, the force is 0. Newton says gravity should ignore light. Gravity should try to grab the light, and its hand should go right through it like a ghost. But Einstein's rocket argument says no, the light must bend. So we have a paradox. How can a heavy object like the Earth pull on a weightless object like light? How can you pull something that has no handle? And Einstein realized maybe we are looking at it all wrong. Maybe gravity isn't pulling the light. Maybe gravity is doing something else. Go back to the rocket. Why did the light hit the wall lower? Did the rocket pull the light? No, the light went straight. The rocket itself moved. The geometry of the room changed relative to the light. So Einstein said, maybe that is what gravity is. Maybe the Earth isn't reaching out and grabbing the light beam. Maybe the Earth is changing the shape of the room that the light is traveling through. The light is trying to go straight. It is doing its best. But the space itself, the very fabric that the light is traveling in, is curved. And a straight line on a curved surface ends up looking like a curve. This was the beginning of the end for the idea of force. We had to stop thinking about muscles and ropes and start thinking about geometry. But how do you curve empty space? That sounds ridiculous. Well, let me tell you about the bug, the geometry of the hot plate. So we have reached a very strange point in our detective story. We have decided that gravity is not a force, it is not a rope, it is not a muscle pulling on things. We have decided that gravity is a curvature. The light bends not because the earth pulls it, but because the space the light is traveling through is bent. Now I can see the look on your faces. You are looking at me with great suspicion. You are saying, Professor, this is nonsense. I can see space. It is right here between my nose and my hand. It is empty. It is nothing. How can you bend nothing? You can bend a piece of wire. You can bend a mattress. But how do you bend emptiness? And even if it is bent, we are inside it. We are trapped in the universe. We cannot step outside to look at the ball. So how can we possibly measure the curvature of the room we are standing in? To explain this, I want to invite you to a dinner party. But this is a dinner party for bugs. Imagine a giant flat sheet of metal, a hot plate. And right in the middle of this plate, we light a fire, a very hot fire. So the plate is extremely hot in the center, and it gets cooler and cooler as you go out to the edge. Now we put our bugs on this plate. These are special bugs. They are made of the same metal as the plate, and they have rulers, little measuring sticks made of the same metal. And we have a law of physics, old-fashioned physics. Heat makes things expand. When the ruler gets hot, it expands, it gets longer. When the bug gets hot, he expands. Everything expands together. So the bug doesn't know he is getting bigger. If he looks at his ruler, it looks the same to him because he grew too. Now let's ask the bug to do some geometry. We ask him to verify the laws of Euclid. We ask him to measure a circle. We draw a circle around the fire. We stay far away, near the cool edge. The bug takes his ruler. He walks around the circle. Click, click, click. He counts the rulers. Since it is cool, the ruler is short, so he has to use a lot of rulers to go around. He writes down a big number for the circumference. Now we ask him to measure the radius, the distance from the edge straight into the center. So he starts walking toward the fire. What happens? As he gets closer to the middle, it gets hotter. His ruler expands. It gets huge. But he doesn't know it. He just thinks, boy, I am covering a lot of ground today. Because his ruler is so big, he needs fewer steps to get to the center. He counts 1, 2, 3, and I'm there. He writes down a small number for the radius of. Now he sits down to check his math. Euclid says that the circumference should be equal to 2 times pi times radius. C equals 2 pi/r. But the bug looks at his notebook. His circumference is huge. His radius is tiny. The equation doesn't work. There is too much circumference for such a small radius. There is more room in the middle than there should be. The bug is confused. He says, my math is broken. But we know the truth. We are looking from the outside. We say, no, Mr. Bug, your math isn't broken. Your geometry is broken. You are living in a world where the scale changes from place to place. And this is what Einstein says happens near the sun. The sun is the fire. But it doesn't heat up space. Space doesn't have a temperature. Instead, the mass of the sun changes, the metric. Metric is just a fancy word for the length of the ruler. Gravity distorts the scale of reality. Close to the sun, a meter is not the same as a meter far away. Close to the sun, a second is not the same as a second far away. So when the earth tries to move, it is like the bug. It wants to go straight. It wants to follow the simplest path. But the grid paper that it is walking on is warped. The ruler keeps changing side. And because the grid is warped, the straightest line turns out to be a circle. The Earth thinks it is going in a straight line forever. But because the space around the sun is distorted, like the hot plate, that straight line wraps around it and bites its own tail, it becomes an orbit. So you see, we don't need force. We don't need hooks and rope. We just need a rule that says mass changes the ruler. Mass tells space how to curve, and the objects just follow the bumps and valleys of that curve. But Einstein was not finished. He had this beautiful picture of the hot plate, but he had a problem. Gravity doesn't just stretch space, it stretches time. Remember the rocket ship? If you put a clock on the floor of the rocket and a clock on the ceiling because the rocket is accelerating, the clock on the ceiling is moving slightly faster through space signals than the one on the floor. Einstein realized that gravity must do the same thing. Gravity slows down time. A clock near the sun ticks slower than a clock far away. So it is not just the ruler that changes size, it is the stopwatch that changes speed. And this is why we call it space-time. You cannot separate them. The Earth is curving through a four-dimensional landscape of warped space and warped time. And now Einstein had the idea, but he didn't have the equation. He needed to write a law that would tell you exactly how much the fire stretches the ruler and slows the clock. And that turned out to be the hardest homework assignment in the history of science. It took him 10 years, and it almost killed him. So we have the picture, we have the idea, we have the hot plate, we have the idea that the sun curves the space around it, and the Earth simply follows the curve. It is a beautiful idea, it is elegant, it makes sense philosophically, but in physics, a beautiful idea is useless unless you can calculate with it. You need to be able to predict exactly where the planet will be next Tuesday at 9 o'clock a.m. If you can't give me a number, you don't have a theory, you just have a daydream. And this is where the tragedy begins, or rather the struggle, because Albert Einstein had the happiest thought in 1907, but he did not write down the final equation until 1915. It took him 8 years of wandering in the desert, 8 years of sweat and headache and wrong turns. Why? Why was it so hard? Because the mathematics you need to describe a curved four-dimensional blob of space-time simply did not exist in the books of physics. Newton used algebra, easy, F equals ma. 3 letters, you can teach it to a high school student. But to describe a curved geometry, you need something else. Think about a bed sheet. If you lay a bed sheet flat on a mattress, it is easy to describe. You can just say it is flat, zero curvature. But now crumple it up, throw some pillows under it, twist it. Now try to write an equation that describes every single hill and valley and wrinkle on that sheet. It is a nightmare. The curvature is different here. It is different. There it is twisted. This way it is stretched that way. You cannot describe it with one number. You need a map. You need a grid of numbers. Einstein realized he was not a good enough mathematician to do this. He went to his old college friend, Marcel Grossman. He said, "Grossman, you must help me or I will go crazy." And Grossman said, "Well, there is this obscure branch of mathematics called Riemannian geometry. Nobody uses it for physics. It deals with curved surfaces in multiple dimensions. It used these things called tensors. A tensor is a beast. Newton's law is one equation. Einstein's law using these tensors is actually 10 equations all tangling up together. It is a multi-headed monster. And Einstein had to wrestle with this monster for years. He would write an equation, realize it didn't conserve energy, throw it away. Write another, realize it didn't match reality, throw it away. He was exhausted. His hair turned gray. His stomach gave him trouble. His marriage fell apart. He was fighting the universe all by himself. But then in November of 1915, he felt he was getting close. He found an equation that looked beautiful. It looked robust, but he had to test it. He had to prove it wasn't just another daydream. And nature had given him a gift, a puzzle. The planet Mercury. You see, for 50 years, astronomers had known that Mercury was misbehaving. All the planets orbit the sun in an ellipse, an oval, and usually that oval stays put. But Mercury is close to the sun. It moves fast. And astronomers noticed that the orbit of Mercury was shifting. It was wobbling. Every century, the oval would turn a tiny, tiny bit. It was a shift of 43 arcseconds per century. That is tiny. It is like looking at a penny from 2 miles away. But it was leading. And Newton could not explain it. According to Newton, Mercury should not wobble that much. Astronomers were so desperate that they invented a fake planet. They said, there must be an invisible planet, let's call it Vulcan, hiding inside Mercury's orbit, pulling on it. They looked for Vulcan for years. They never found it because it wasn't there. So Einstein sits down at his desk. It is 1915. He takes his new terrifying equation of general relativity. He puts in the mass of the sun. He puts in the distance of Mercury. He calculates the curvature of space near the sun. And he asks the equation, how much should the orbit wobble? He does the math. It is pages and pages of calculation. He gets to the end. He sums up the number. And he looks at the result. The number on the paper is 43. 43 arcseconds. Exactly. Precisely. To the decimal point. Can you imagine that feeling? He is alone in his room. He hasn't looked through a telescope. He has just been scribbling symbols on a piece of paper. And those symbols reached out across millions of miles of space and described the motion of a planet perfectly. A motion that had baffled the greatest minds for half a century. Einstein later said that when he saw that number, he had heart palpitations. He felt like something snapped inside him. He was so excited he couldn't work for days because he knew at that moment he didn't need to ask anyone else. He didn't need a Nobel Prize. He knew that he had heard the whisper of God. He knew that gravity was not a force. He knew that space and time were curved, and Mercury was just following the twisted path of the valley near the sun. Newton was overturned. The mystery of Vulcan was solved. But Einstein wasn't done. Mercury was just explaining something we already saw. To really win, to really prove he was right, he had to predict something that nobody had ever seen before. He had to bet the farm on a prediction that seemed impossible. He had to bet on the eclipse. So Einstein has Mercury. He has the numbers. He knows he is right. But in science, you have to be careful. It is not enough to explain the past. Anyone can fit a curve to old data if they wiggle the numbers enough, and that is cheating. To really win, to really prove you know the secrets of the universe, you have to predict the future. You have to bet your reputation on something that nobody has ever seen before. You have to put your head on the chopping block and say, if I am wrong about this, my whole theory is trash. So Einstein looks at his equation and he says, light. Remember the rocket ship? We said that gravity must bend light. Well, the sun is a very heavy object. It creates a deep valley in space. So if a star is shining behind the sun and its light passes right next to the edge of the sun on its way to Earth, that light should fall into the valley and curve. Now here is the drama. If you use Newton's theory and you squint and you pretend light has a little bit of mass, Newton predicts a tiny bend, a shallow curve. But Einstein's theory, because it curves both space and time, predicts to double the bending. So we have another contest, a heavyweight fight. In this corner, Isaac Newton. He says the star moves a tiny bit. In this corner, Albert Einstein, he says the star moves a lot. Nature has to decide. There is no arguing. We just have to look. But there is a practical problem, a big one, Nasir. To seize this bending, you need to look at a star that is sitting right next to the sun in the sky. But if you look at the sun, you go blind. The sky is blue. The sun is blazing. You cannot see stars in the daytime. So how do we perform the experiment? We have to wait for nature to help us. We have to wait for a total solar eclipse. We need the moon to slide in front of the sun, block out the fire, turn day into night, and let us see the faint little stars right next to the rim of the sun. In 1919, a British astronomer named Arthur Eddington decided to settle the bet. Now, I want you to think about the context here. The world had just finished fighting World War I. England and Germany were enemies. They had been killing each other in the trenches for years. And here is a British scientist, Eddington, traveling to the coast of Africa to test the theory of a German scientist, Einstein. It is a marvelous moment. It shows that science transcends borders. Science doesn't care about your nationality. It only cares about the truth. So Eddington goes to the jungle, to the island of Principe, and it is a disaster. It rains all day. Clouds everywhere. He is terrified. He has traveled thousands of miles, carrying these heavy telescopes, and he might see nothing. But at the last moment, the clouds part. The moon covers the sun. The sky goes dark. The stars pop out. He takes the pictures. Click, click, click. He brings the photographic plates back to England. Now, what is he looking for? He takes a picture of the stars without the sun. That is the true position. Then he puts the eclipse photo on top. If Einstein is right, the stars near the sun should look like they have been pushed away. Because the light curved around the sun to get to us, our eye traces it back in a straight line, and we see the star in the wrong place. Eddington measures, he gets out his ruler, he compares the dots, and the result comes in. The stars had shifted, and they didn't shift by the Newton amount. They shifted by the Einstein amount. The light was bent, space was curved. When the news came out, it was absolute pandemonium. The headlines the next day were huge. The New York Times wrote, "Light all askew in the heavens, Einstein theory triumphed." Overnight, literally overnight, Albert Einstein went from being a quiet professor to being the most famous man on earth. He became an icon. You know, the hair, the face that started here, not because he invented a gadget, not because he built a bomb, but because he changed our fundamental understanding of where we live. He showed us that the space we live in is not a fixed wooden stage. He showed us that the universe is flexible. It is like a fabric that ripples and bends and twists. He showed us that the thing we call gravity is just the shape of that fabric. It was the death of the old physics and the birth of the new. And you know what Einstein said when they sent him the telegram, when they told him, "You were right"? He didn't jump up and down. He didn't scream. He just smiled and said, "I knew it was right. The theory is too beautiful to be wrong." And there is always a but. Once you accept that space can curve, you open the door to some very scary things. Because if the sun curves space a little bit, what happens if you have something heavier? What happens if you curve space so much that it rips? Let's talk about the black holes. So we have opened the door. We have proven that space is flexible. We have proven that mass curves geometry. And everybody is happy. We have a new theory of gravity, and it works perfectly for the planets and the stars. But in physics, you have to be very careful when you write down a new law, because sometimes the mathematics is smarter than you are. Sometimes the equations tell you things that you didn't intend to say, things that seem crazy. Right after Einstein published his theory, a man named Carl Schwarzschild took a look at it, and he asked a very dangerous question. He said, "Okay, Einstein, you told us that the sun curves space like a gentle valley, and that is fine. But what happens if I take the sun and I squash it? Imagine we have a trash compactor, a cosmic trash compactor, and we take the sun, all that mass, all those millions of tons, and we squeeze it. We squeeze it down until it is half its size. Then we squeeze it again. We keep squeezing until the sun is only 3 miles wide, the size of a small town. Now the mass is the same. It is still the sun. But the density is monstrous. And the curvature, the valley in space is no longer a gentle slope. It has become a bottomless pit. The sides of the valley are vertical. Now think about the rule we learned earlier. The speed of light is the limit. To escape the Earth, a rocket has to go 25,000 miles per hour. That is the escape velocity. If you make the Earth heavier, you have to go faster to get out. But if you crush the sun down to 3 miles wide, the gravity becomes so strong, the valley becomes so steep, that the escape velocity becomes greater than the speed of light. Now put 2 and 2 together. Nothing can go faster than light. You need to go faster than light to get out. Conclusion, nothing gets out. Not a rocket, not a particle, not even light itself. If you shine a flashlight up from inside this hole, the beam of light tries to climb up. It slows down in energy, and it falls back in. It is a trap, a one-way door in the universe. You can check in, but you can never leave. From the outside, it would look like a spot of pure darkness, a hole in the fabric of reality. We call it a black hole. Now, you have to understand, when Einstein saw this, he hated it. He absolutely hated it. He said, "This is just mathematics. This is a quirk of the numbers. Nature would never allow such an abomination to exist." He thought there must be some law that prevents a star from being crushed that small. He spent years arguing that black holes were impossible. But nature doesn't care what we think is impossible. Nature follows the laws. And the law says, if you put enough mass in a small enough box, you break the floor. You rip the space-time. And now we know they are real. We see them. There is a monster sitting right in the center of our own galaxy, weighing 4 million times as much as the sun, eating stars for breakfast. The math was right. Einstein was wrong to doubt it. But that wasn't the only monster hiding in the equation. There was an even bigger one, the biggest one of all. Einstein decided to take his equation and apply it to the whole universe. He wanted to build a model of the entire cosmos. And he found something very disturbing. His equation told him that the universe cannot stand still. Think about it. Gravity is a pull. It attracts. If you have a universe full of galaxies and they are all pulling on each other, the universe should be collapsing. It should be shrinking like a balloon losing air. Or if it had a big kick at the start, it should be expanding. But it cannot just sit there, static and unchanging. Gravity won't let it. But Einstein, he was a man of his time. He believed in the fixed universe. He thought the universe was eternal. It had always been there. It would always be there. So he cheated. He actually went into his beautiful equation and he added a fudge factor. He added a term called the cosmological constant. It was a made-up pushing force to counteract gravity and hold the universe still. He forced the math to match his prejudice. And then a few years later, a man named Edwin Hubble looked through a telescope. And what did he see? He saw the galaxies rushing away from us. He saw that the universe is expanding. It is getting bigger every day. If Einstein had just trusted his own equation, he would have predicted the expansion of the universe before anyone saw it. He would have predicted the Big Bang. Because if the universe is getting bigger today, that means yesterday it was smaller. And 1 billion years ago, it was tiny. And 13.8 billion years ago, it was all at one point. Einstein called that fudge factor the biggest blunder of my life. But I don't think it was a blunder. I think it shows us something important. It shows us that even the greatest genius is human. And it shows us that the laws of physics are not just inventions of our mind. They are real. They are out there. And if you listen to them, really listen to them, they will tell you the history of the universe. So we have gone from a falling elevator to the birth of the cosmos. That is the power of an idea. So where does this leave us? We have come a long way in the last hour and a half. I want you to stop and look at the path we took, because the path, the road itself, is just as important as the destination. Remember where we started? We didn't start with complex equations. We didn't start with computers. We didn't start with telescopes looking at the edge of the universe. We started with a daydream. We started with a man falling off a roof. We started with a man in a box floating in deep space. Cool. It was a tiny, simple idea, the idea that falling and floating are the same thing, the idea that gravity can be erased if you just let go. It is an idea that a child could understand. And yet when Einstein took that little seed and planted it, look what grew out of it. He watered it with logic. He fed it with mathematics. And it grew into a tree that covers the entire universe. It grew into the bending of light. It grew into the slowing of time. It grew into the expanding universe and the Big Bang. It grew into the monsters in the dark, the black holes, all of that complexity, all of that magnificence was hidden inside that one simple thought. And that, to me, is the beauty of physical law. It is not that the universe is complicated. It is that the universe is built on a few deep, simple principles that play out in infinite variations. You know, people often ask me, Professor, doesn't science remove the beauty of the world? Doesn't explaining the rainbow make it less magical? And I say, no, it adds to the beauty. To know that the rainbow is made of light, obeying the laws of reflection and refraction, to know that the sensation of weight on your feet is actually the curvature of time, that makes it more marvelous, not less. And there is a lesson here, a lesson for all of us. The lesson is that nature is far more imaginative than we are. If I sat in a room by myself and tried to invent a universe, I would never have come up with curved space-time. It is too crazy. I would have made it simple. I would have made it flat. But nature, she has a better imagination. She dreams up things that we could never guess. And our job as scientists, as human beings, is not to tell nature how she should behave. Our job is to listen, to look, to be surprised. We are just the audience, watching the greatest show in existence. I am still amazed, and I think I will always be amazed that such a simple idea, the equivalence of falling and floating, could lead to such a magnificent structure. It turns out that the man falling off the roof wasn't falling down. He was falling into a new understanding of who we are and where we live. It is a wonderful world, and I am glad we figured out a little bit of how it works. Thank you.